expert, international expert with us, Dr. Prashant Saxena sir. Currently, Professor Prashant Saxena is a senior lecturer in the James Watt School of Engineering at University of Glasgow, Scotland, UK. Before that, sir, basically he is interested in understanding the complex behavior of soft solid due to deformation under extreme multiple physical conditions. Dr. Saxena has undergraduate degree in mechanical engineering from Indian Institute of Technology, Kanpur. In mechanical engineering from Indian Institute of Technology, Kanpur, and a PhD in applied mathematics from University of Glasgow itself. He has received postdoctoral training from University of Nuremberg and Lausanne. He also worked as an assistant professor in Indian Institute of Technology, Hyderabad. And Dr. Saxena has received several awards for his work, including the New Investigator Award from EPSRC, Ramanujan Fellowship, that is a very prestigious one, from SERB, and a gold medal in the Indian National Olympic Physics Olympiad. So words are not limited to explain his work. He is continuously writing a good paper in International Journal of Repute. So we all, let's welcome Dr. Prashant Saxena sir with us. Welcome sir.
Yes, okay. Thank you. So, apologies for the issues in the beginning. Thank you very much to everybody who is here, those who are sitting in the classroom and those who are joining us online. Thank you for making this course happen. And I would like to personally thank Professor Aman Khurana for organizing this nice meeting and inviting me to speak, give a few lectures in this. As he said, I have been working in this field for many years now, and I find mechanics of soft solids, nonlinear mechanics quite interesting, and I hope that during this few days I'll be able to share my enthusiasm with you, as well as we can learn a few things together. So the way I would love to have this course is if we can have a bit more interactive session. I think I've lost your video somehow for the classroom. So I would love it to be a bit more interactive session rather than me just going on talking about things. So I highly encourage you to please stop me when something is not clear and just ask questions. Either you can raise your hand in the classroom and then we can take your questions directly, or you can just type in something in the chat box. And then we can take it forward. So, can I quickly ask the local organizers? I'm not able to see the video of the classroom anymore. Can you fix that, please? People who we are talking to, it becomes very hard to just keep on speaking to a blank screen. So that's why it's nice to have some feedback from the people who are there. And also the participants who are joining online, please turn on, if you can. It will be very nice if you can turn on your video. So. It becomes much nicer if we can just see each other while we are discussing something. Okay, so the classroom video I can see now. And yeah, people who are online, please feel free to turn on your video as well. It will be nice to just have your feedback. Okay, so you have already had some initial introduction to this topic in the morning session. So I understand you already know that big topic of the course on why mechanics of soft material is important and so on. I just want to give you like a couple of slides of introduction, and then I will move on to a bit more detailed discussion. Right. So let me try to share my screen. Right. Okay, so hopefully you can see my screen. And I'll just move on to directly to some examples. I'm not going to talk a lot about the introduction. I just wanted to show you a couple of examples of the kind of materials and systems that I've been working with. Okay? So the two essentially the types of systems that I like to study are systems or soft materials where you have interactions between electromagnetic field and the mechanics of the materials itself. So one of those kind of materials is magnetoactive soft solids, and you can see some of the pictures on the slide here. the central idea, and they are a lot more complex and very interesting system, but I'm just giving you the very basic fundamental idea of the system is that you have some sort of a rubber material, as shown here, and which is what we call as a matrix, and then you've got some, let's say, ferromagnetic particles. So in this case, it is iron particles, but then you can have different types of particles, and they are all microscopic in nature. And when you apply a magnetic field, then they can deform significantly. And because the matrix is very soft, the matrix can be made of rubber or hydrogels or some other kind of elastomer. Because the matrix is very soft, they can stretch a lot. And that large stretch basically is very useful in designing certain applications. So in the bottom figure, you can see there's a whole host of millimeter scale robotic mechanisms that have designed that they can control from a distance. They can bend and they can roll inside a fluid environment. So this is like one of the ways where soft solids are being used in robotics. So on the figure here, it's kind of a vibration absorption system where the vibration, the characteristics of the vibration can be understood by tuning the stiffness of the magnetoelastomer here. So you can change the stiffness by applying a magnetic field. You can tune that, and based on that, you can basically isolate a lot of vibration. This is another system where basically it's a valve that just opens and closes based on magnetic field. So magnetic field is just an example here. It's not the core idea, but it's a way where mechanics can be enhanced and multiple with additional variables. There's another kind of system that I'm quite interested in is electroactive materials. And here what happens is, again, this is based on extremely large deformation. And by the way, we'll study these systems in detail. I'm just giving you just a brief overview right now. And based on the softness of this dielectric material that is right here, it's like a soft elastomer that you can deform significantly in the presence of electric field by applying electric field. You can operate either as an actuator, or you can operate as an energy conversion system. So you can operate in both the directions. So the example down here is often a pump. So basically the active dielectric membrane is used as a pump. So the actuation mechanism is quite important here. So let me stop sharing here. Right. So this was just like a couple of examples where I think soft materials enhanced with additional variables, with electric field or magnetic field, can lead to some interesting ideas. There is an entire field of robotics or of engineering where people like to take inspiration from nature and design new mechanisms or new products based on that inspiration, right? And if you look around us, then, for example, if I just look at my fingers here, so my fingers are made of, the tip of my fingers are made of a soft tissue with muscles inside of it, and it's multifunctional. So it can act as a gripper. It can grip certain things. But at the same time, it can act as a pressure sensor. So it understands how much pressure I need to apply to grip something, and it also acts as a temperature sensor. So this soft you can call it a soft system has multiple functions. It's a temperature sensor, it's a pressure sensor, it's a gripper, and if you look around in nature, pretty much everything which is in living systems, whether it is plants or animals, is primarily made up of soft materials and has multiple functionalities inside of it. So this is where we are coming from, and this is what we basically want to study in a bit more detail. And if we can design engineering systems which can have multiple functionalities at the same time, instead of like you can see this door or this wall behind me, which is made of a very stiff material, it has a single functionality. So that's where the motivation comes from. And then when we see that we have to study the mechanics of these soft materials, the primary thing is that they can undergo very large deformations, extremely large deformations. And because they can undergo extremely large deformations, we need to use a different set of mathematical principles to study them properly. So I just want to focus on those principles in the initial part of my talk, in the first couple of days. So what I'll do is I'll just share my screen again, and then hopefully we can. Right. So can I quickly check if my screen is visible? Okay. So the things that I want to basically talk about is in the next few couple of days, just to begin with, is the principles of continuum mechanics. I need to take a small one. And so continuum mechanics is just a study of basically trying to study all these things systematically. And within this, there are a few topics that I want to touch at. So first of all, we'll look at tensors, both tensor algebra and tensor analysis. Then we just look at mechanics in general. What are the various principles that we use for looking at solid mechanics? I want to touch a little bit on differential geometry. And the most important bit, in my opinion, for study of mechanics is variational calculus. Variational calculus sort of comes into picture everywhere, no matter what kind of physics that you study, whether you study the kind of physics that we are doing in continuum mechanics or relativity, or whether it is classical physics or quantum physics, you'll see this variational calculus popping up everywhere. So I think it is one of the most important topics if you're a student of this domain. And then finally, once we have done continuum mechanics, we'll go and look at some applications in electrocoupling and magnetocoupling. Okay. So this is what we saw in the beginning, electro and magnetocoupling. And another important thing that I want to focus on is stability. And we'll discuss more of this as we come along in the course. So that's the plan for the course. I hope, and maybe somebody can just tell me here. I shared a bunch of study materials as well with the organizing team, including a set of notes that I prepared and some of my research papers. So this initial portion on continuum mechanics is going to very closely follow a set of notes that I have prepared, which are going to be part of a book that will be soon published. So I strongly recommend that if you have those notes with you, you can basically have them in your hands while we are studying. a lot of what I'll do will be based on writing down and basically on the slides. Not showing you PowerPoint slides, but basically writing down things on this Blackboard environment. So if you can just take notes or work alongside, that would be quite nice. Okay, so that's the basic idea, and that's how we will start. Any questions before we move on to the first topic? And please feel free to there's somebody who's raised their hands. Please go ahead.
Good afternoon, sir. I just want to know, maybe have some MATLAB codes that gives the result for these kinds of applications.
Yes, we can discuss. I can discuss with Professor Aman Purana, and then we can provide something similar to you. I think maybe Aman can say, do we have some assignments in lab as well?
In the last I am having a tutorial and part of that, so I will have giving some MATLAB code also for the basic that we are covered.
So that's very
I
helpful.
will
Thank
share
you.
with the all.
Thank you. Yes. Anything else? Okay. So I'll just quickly share my experience with teaching so many years. This kind of teaching works really well if we kind of have a back and forth. So if you can just raise your hand or ask questions or maybe give comments on something that I have done wrong, it will be very, very useful. And that's how we can move forward. The other thing that I want to say is the goal of this the next 5 days is not for me to come and write a lot of things, because majority of what I would speak up is present in a lot of books here. So you can see things in standard textbooks. But the idea for this course is that yes, there are things in textbooks, but there is a lot of value in you and me talking and figuring things out. So that is the key importance of this course, that if we can discuss and if we can talk, it doesn't matter how much material we cover during the lecture, because the notes are already there with you, the books are already there with you. It's more about our interaction. So again, I would highly recommend stopping me talking about talk about things and ask questions. Okay? So feel free to do that. I love being interrupted. Right. So having said that, maybe let's begin with the first thing, that is tensor algebra and analysis. Okay? And my handwriting is a little bit ugly, so forgive me for that. Hopefully, the mathematical things will be fine. English is quite bad. Okay, so tensors basically form the fundamental mathematical object using which we work on a lot of things. So I was discussing the people who are there with Aman, and he told me that there are around a third of you are master's students, a third of you are PhD students, and there are maybe a couple of faculty members. So my apologies to faculty members, because the things would be probably simple for you, but I think that for students, especially who are in the master's or PhD, I hope that you will find something interesting here, and then you can again see what goes on. Okay, Aman, I think I've again lost the video of the feed. Okay, there it is. It's back. Sorry. Okay, so we'll start with tensor algebra and analysis. And tensors, some of you who are studying mechanics might have come across tensors in many ways. So some of you already know that stress is a tensor, strain is a tensor. Stiffness of a material is often expressed as a tensor, and there is no limit to that. And then the question comes, what exactly is a tensor? because when I was doing my master's and PhD, I was heavily confused by this question. So I like to address it head on, and maybe so that at least one thing you learn from this course is what is a tensor and how do I work with tensors. Okay? So to understand tensors, we need to understand vectors first. Okay? And I know that everybody knows what a vector is, but we want to do a little bit more mathematical definition of it. So, and please don't get discouraged by the mathematics that comes in, because that's very essential, and it's also not hard. Once we look at it carefully, it's not really hard. So a vector, I think we are kind of familiar with in physics is that, okay, if something has a magnitude, has a direction, that is a vector. So like a velocity is a vector it has a certain magnitude, which is speed, and it has a direction. But for mathematicians, that's not sufficient. So for mathematicians, they define vectors as something that is part of a vector space. Okay? It's an element of a vector space. Okay, so now the question is, what is a vector space? And that's a good question, because that's when we start to get somewhere. Okay? And by the way, all of this is from chapter 1 of the notes that I've shared with you. So you can go and see everything is there. Okay? So the vector space is again a very key concept, and we can't move forward without that. So let's take what is the vector space. Okay? So vector space is basically just a set of elements. So let me write it this way. Okay? It's a set with some key properties. And the key properties are that let's call it V. Okay? So the key properties are that is that 0 belongs to V. Maybe let me not be very mathematical here. Let me talk about something a bit more physical. So the key property is that if you choose any two elements from vector space, any xi and xj from vector space, then a linear combination alpha xi plus beta xj, which is called as a linear combination, is part of that set again. That's the key property, and let's see why that is important. Okay. So if I take my set, let's say if I take the entire real line. So what is a real line? Real line is basically a set of all the numbers from minus infinity to infinity. So if I choose any two numbers, x1 and x2, which are on the real line, then I know that any combination of them, alpha x1 plus beta x2, is a part of real line. So if I take the entire real line, that's going to be a vector space. But if I choose, let's say just a set which is let's say between minus 10 and 10, then this will not be a vector space, because you can choose 7 and 8, which is 15, which is not an element of S, right? So So that's the key idea of a vector space, that and a lot of other things basically boil down from it. So zero, for example, zero automatically becomes part of a vector space because you need zero to be there. And then you can kind of start thinking in terms of how do I define vector in a bit more careful manner. And by the way, this set which we said here is not necessarily just numbers. It can be other things as well, as we will see later. So let me give you a few more examples. So from this example here, we can see that it's kind of obvious that if you can add any linear combination, then you need to go all the way up to infinity. You can't stop somewhere in between, right? So if I draw, let's say, more visual diagram. So let's say this is your coordinate system. This is your x-axis. This is your y-axis. So far, what we had seen was the real line was basically along here. So this was a real line, and this was a vector space. But nothing stops you from having, I don't know, this line here, which goes all the way to infinity. And this is also a vector space. I get a message that this meeting will end in 5 minutes. Can we change that amount?
Yes, sir.
Yes, sir. We are going to extend. Okay. So if you take this, if you look at this colorful line that I just drew here, and if I just take any point here on this line, maybe let's a point on here and a point on here, and these are basically just two vectors, and if I add them, if I take any linear combination of them, it's going to stay on this line itself. So this entire line itself is a vector space, right? And the key property that makes it a vector space is, first of all, it passes through 0, and then it goes all the way to infinity in both directions, right? If I drew a line like this here, which does not pass through 0 but goes all the way to infinity, that is not a vector space. Right? So this is some of the interesting key concepts that I think we should become not just familiar with, but also kind of develop intuition for, that what makes thing a vector space, and therefore why is this a vector and why is that not a vector. So this is, you can see in terms of coordinate lines. We can also see in 2 dimensions. So there is something called as R2, and those of you who are doing maybe a bit more advanced mathematics may be familiar with these notations, R3, R4, and so on. So basically, R2, R3, R4 is just 2-dimensional or 3-dimensional or 4-dimensional spaces. So this is what we are quite used to in physics, where you've got any element x is like x1, x2, x3. Right? It's a vector with 3 dimensions, with 3 components, and so on. So these are all vector spaces, R2, R3, R4. But then you can again see why they are vector spaces, because if you take any 2 elements, you add them up, you stay in the same space, so it becomes vector space. So the question that you can ask me is, why do I need to know about vector spaces because you said we are starting with tensors. And I think we will come to that answer very quickly. But let me give you another example, which is quite interesting. So take a set of all functions, linear, or maybe be a bit more precise, first order polynomials. So for example, this set is basically a lot of functions. And I'm being a little bit loose with mathematics just now, but we don't need to be very precise. And these functions are such that f of x equals alpha x plus beta. So now we are no longer dealing with numbers, right? In the previous example, we had these numbers or vectors in the two-dimensional space or three-dimensional space. Now we have come to functions. And we've got functions which are of this form, alpha x plus beta. So for example, you can have f of x equals 2x, f of x equals, I don't know, 1, f of x equals 3x plus 5, all kind of examples like this. So if I make a set of all the functions which have this property, then that becomes a vector space, right? So that becomes a vector space. Because you take any of those two functions, multiply with them with anything, add them together, you will get something that is part of the same set. Right? So often this is also sometimes called as function space. Okay, so this is where we were. We were talking about what makes something a vector space and what is not a vector space. So the last thing that I said was that for this particular set, which was made up of all the functions which were just first order polynomials, if you make a set of all of those functions, then that becomes a vector space, and that vector space is sometimes also used, we call it as a function space, right? So vector space can be basically collection of anything. It can be these traditional ones that we are familiar with, or these kind of function spaces that we have been using. Any questions so far before I just move on to the next thing?
Class, you can be very interactive. If you have anything to ask, you can ask. In between, you can ask.
Okay, maybe let me quickly talk about the next important bit here, which is the basis. So basis of a vector space is basically just the minimum number of elements that you can collect, so that every other element can be expressed in that form, right? So for example, in R2, which is basically all of your xy plane, if I take a vector, call it E1 here, take a vector, call it E2 here, then this set E1 and E2, let's call it G. So this is a basis, right? So I think you're familiar with this part. I can take any vector now, any vector V can be written as, alpha E1 plus beta E2. So the concept of basis is quite simple, that you just take any two, and these need to be linearly independent. You take a set of or a collection of those vectors using which you can express anything based on that. So in the case of function space here, for this one, you need two functions to form the basis, right? So here the two functions can be 1 and x. And now any function can be expressed using these bases. So right. And basis, there are infinitely many different types of bases possible. But that's a central idea for what we have as a vector space. I mean, you can have another, let me give you another example. You can have a vector space of all quadratic functions. And in that case, the basis would be basically just 1x and x squared. You can have a vector space of all sine x. And this is not a very mathematically precise way of writing it, but I'm just, just writing it just to explain that. So this would be, 0 sine x, 2 sine x, minus and so on. So the basis would simply be sine x. So in this case, if you just see, all the different functions would be, this is sine x. Oops, something. This is sine x. Sorry, there's a problem, I think. It's just deleting automatically. If I do too much, it deletes. So this is sine x. Then let's say this is 2 sine x, and so on. I mean, so if you take a collection of all such functions, it again makes a vector space. And this is something that I basically want to. I'm repeating this again and again because I think this is a very important part to be familiar with. That you can have vector spaces with numbers and with functions, and with later on you will see you can have it with other objects as well. But this is just to make you aware that the mathematics behind this is very abstract, and we can do a lot of interesting things with this. So now the question comes. Okay, we started with the question of tensors, right? And now we at least understand what a vector space is, and then now we want to understand how do we understand tensors using this concept of vector space. So tensor is something that you can simply think of like a function. Okay, so function has an input, has an output, and function I'm sure you're all familiar with in maths. Tensor is just a function, but it's a function that has an input is something from a vector space, and output is something from another vector space. Okay? So tensor is something that inputs takes something from one vector space, let's call it V1, and gives you something from another vector space V2. Okay, and this operation, sometimes we call it as an operator as well. So this operator that takes something from a vector space, gives you another thing from another vector space is a tensor. And what is the important bit is that it's a linear transformation. And linear transformation simply means that you can look it up. It basically means that linear combinations are satisfied. So there is nothing non-linear going on here. Linear transformation is the simplest type of transformation that is there. So that's the idea. So why do we say stress is a tensor? The stress is a tensor because it takes something from a vector space and gives you another output of the vector space. So what does it take in? So you might have seen this picture from your mechanics courses, but let me draw it again. I think you might have seen this in mechanics of materials. If you have done advanced mechanics, you might have seen this here. So let's say this is a body, and it is fixed at some location, applying some forces somewhere else, and this body is under stress. It is experiencing some internal forces, right? So what I do is maybe if I take, it's a virtual plane. If I make a virtual cut in the body by a virtual plane, it will basically cut through the body via a surface, right? And if I look at that surface, let me draw this surface here, and I pick up a point somewhere here, a small region on that surface. Then there is something which is a normal vector. Normal vector is basically just describing the orientation of the surface. And then there would be, for this small element, let's call it dA, there would be some force which is what we call as traction. Okay? This is traction on that tiny bit of element. So this traction is, sorry about this. Yeah. What we call as so let me just rewrite my ideas, and let's see, this is the force, and this is the traction here. I'll repeat the ideas. So we just made a virtual cut in a stress body, and then we had we took like a small point, small region from that plane. There is a normal vector, and there is a force vector, normal vector and force vector, and then based on that we define a traction vector. So the stress, how does stress come into picture? Because it's all about, stress is something that tells you about internal forces inside the body, right? So stress is a tensor that links these two vectors together. So the stress tensor, let's call it sigma. It basically says that if I operate on the normal vector, I will give you the traction vector. Okay, so stress is an operator. So input is vector space, basically vectors of directions. And the output is another vector space, which is basically vectors of forces. Okay? And now you can imagine that, okay, based on this normal vector, you can have different types of traction at the same point. So you can have, I don't know, maybe another you can have another plane at the same location with a different direction passing through the same point, and then that would have a different normal vector. So this normal vector is N2, and the traction corresponding to this is T2. So you'll have T2 is sigma times N2, right? So the sigma is the same. This sigma and this sigma is the same. So the tensor stays the same. This tensor contains the information about all the forces and all the directions. You give an input as a direction and you get an output as a force. And that's how tensors become quite important in this domain, because they start linking. You can start talking about vector spaces, and you can start talking about abstract objects. So sometimes you might see that stress is expressed in this form, right? Sigma 11, sigma 12, sigma 13, sigma 21, 22, sigma 23, sigma 33, and it is symmetric. So this is basically just a what we call it as a matrix representation. And a lot of my students, and in fact when I was a student, I was always confused between the concept of a matrix and the concept of a tensor. Okay? So here we can kind of attack that again head on and say that the matrix representation, so a stress, any tensor can have infinitely many different matrix representations. The matrix representation depends on the choice of coordinate system. So, if you have x1, x2, x3, but at the same time you can have a different one, maybe a different color. x1 prime, x2 prime, x3 prime. And depending on what coordinate system I choose, this matrix will change. But the physical quantity, which is a tensor, it stays the same, right? So matrix, the way you write down the matrix just depends on the coordinate system, and I think this is something you might be familiar with when working with vectors. That you change the coordinate system and just the numbers there changes, but it just depends on the user. Okay, so that's why it depends on the user. All right. So this is where we are. Any questions so far? I think we covered some very fundamental stuff here. I'll maybe pause for a couple of minutes and see if there are any questions around.
This is very, very important concept of stress.
Okay, if not, maybe we can move on.
Sir, there is one question, sir.
Yeah, carry on.
Divyansh, you can ask.
Sir, actually you said it is a linear transformation. So this is linear transformation n cap to t cap, no?
So sorry, can you speak closer to the mic? I can't hear you from there.
Am I audible?
Yes.
Sir? You said it is a
Yes, you are now.
It is a linear transformation. So it will be always like
Yes.
sigma is the operator that is transforming n to t.
That is correct. Sigma is the operator that is transforming
But-
M to T. Yes.
Initially, you said it is a linear vector space is a linearly dependent, but you also give the example of one x and x square, also the sin x. These are not the linear function. How it is like then basis functions are linear?
Okay. So let me go back to that. That's a fair point. So when I said that this transformation is linear, what I mean is that when you go from the input to output. So let's discuss that point. I think that's a good point. So when I say the transformation is linear, it simply means that let's say the tensor is A. Okay, this is the tensor, and it takes in some element from a vector space, and it gives you another element from, let's V1 and V2. Okay, so y equals A times x. So when I say the transformation is linear, linear means that if I take in two elements from this V1, alpha x, and a linear combination of that, alpha x2, sorry, beta x2, and then operate A on them, what that will be equal to is alpha times ax1 plus beta times ax2. So this is basically what is meant by a linear transformation, that it does not matter what the input vector is. The input vector can be your vector in a R3 space, the input vector can be a function in the function space, your input vector can be a quadratic function or a sinusoidal function. It does not matter what the input vector is. What matters is how the transformation happens. Okay? The transformation happens in a way that anything that was all this combination inside, so either you can add all your input vectors first and then do the transform, or you can do the transform first and then add your input, then add the resulting vectors together. Okay, so the way the transformation happens is linear. This is what we mean by linear transformation. But the input x1 here, so this input vector x1 can be function of f of x, which is sin x plus cos x, something like that. It can be anything. I don't care what so this is the input vector. I don't care what the input vector is. It's just the way the transformation happens is linear.
Vector space.
Does that answer your question?
It answers, but vector space can be linear, non-linear also, no?
So vector space, the elements of vector space are just the elements of vector space. For them, we don't have this distinction between linear and non-linear. Okay? So when I talked about this function space here, so all these, the linear function, the quadratic function, the sine functions, these are all just vector spaces with collection of functions, and of course these functions are non-linear. But when we talk about the elements of the vector space, we do not need to classify them as linear or non-linear, because that classification generally is not required. But yeah, you can call them whatever you want. But no, it does not matter what the elements are in the vector space. They can be anything. As far as a tensor operator is concerned, they can be anything. Yeah, please carry on. You were saying something else as well, I think.
No, sir, it's okay. I got the point, sir. No, sir, it's okay. I understood.
Okay, thank you. Is there anyone else? I think that was a very nice question. Thank you. Okay, maybe we see a few more things as we move forward. So let me. Microsoft is always a problem. Okay. So the tensors can operate on different types of vectors, different types of vector spaces. Let me give you another example. So right now what you saw was E equals sigma n, right? This is a very common occurrence in mechanics where we work with stresses, and this is often like a matrix multiplication. You can have many different types of tensors. You can have a very commonly used is identity tensor. You might have seen that where basically you operate this and you get the same vector. You can write vector product, cross product as a tensor. In fact, this is something that comes up quite often in if you're dealing with, like, let's say, advanced concepts in continuum mechanics. So let's say you have a vector in a vector space, and you have another vector z in another vector space, and z is basically operated by a cross product between w and x. Okay. So you can write this thing as w times x. So you can say this cross product is basically represented like a tensor operation, and sometimes it is quite useful in many different problems. So this w is just a tensor. It takes in a vector small x, gives you an output as vector z. By doing this cross product. You can also have now as I said, I mean, vector space can be made with many different types of quantities. So you can have a vector space of stress tensors. Let's give it a small interesting variable. And then you can have a vector space of strain tensors. Let's call it E. So it is basically, it has lots of, all the different possibilities of stresses. It has all the different possibilities of strains. And then there is a tensor, what we call as a stiffness tensor. Which is fourth order. Now we'll talk about the order a little bit later, but some of you might know it's a fourth order tensor, which basically is represented like C, and you get that if you operate C on strain, you get the stress tensor. Okay, so tensor, now this is like a higher order concept where a tensor operates on strain to give you stress, and strain is now a member of a vector space. Stress is a member of a vector space, and the relationship between them is via the stiffness tensor. And if you have taken any course in finite element method, or maybe studied some other advanced mechanics, you might have seen the stiffness tensor coming to picture. You might see this as CIJKL. This is a more common way of looking at in different books. This is exactly the same thing. It's a stiffness tensor, but it takes in a tensor as an input and a tensor as an output. But because these tensors are members of a vector space, you can actually do that. So these are some different applications of tensors that we can see. Now I want to talk a bit more about these. but I'll check with the host. Do we have a break at some point? You said, Aman?
Yes, sir.
What would be an
We are
appropriate time?
planning to have some small tea break at around 3 here.
So in 15 minutes?
Within 15 minutes, sir. After 15 minutes, we will have that break. Short break.
Okay, so fine. Yeah, so we will we'll carry on, and then in 15 minutes we have a short break. Okay, so right, so as I said, I mean, we can always have a matrix representation of a tensor based on the choice of coordinate system, and that's why we have we want to work with some quantities called as invariants. And these invariants become very important when we look at material properties and when we look at other things later on. The idea of invariant is that, by what the name suggests, it does not change. So it does not change with coordinate system. So as I said before here, what is that? Yeah, that the matrix representation of the tensor depends on the choice of coordinate system. So sigma 1, sigma 1, 2 here will depend on what your coordinate system is. But often we need quantities that do not depend on that. So that's why we want to have something called as invariant. So we'll talk about invariants a little bit, but before that I just quickly want to touch upon order of a tensor, right? So I briefly said that. So I think you can get some intuitive idea behind this concept, and this basically applies to tensors which are operating on the vectors that we know from the traditional sense, the vectors from the coordinate system, and not the function space. For function space, we have a different way of looking at it, but the tensor that we're operating on the usual vectors, and I'm not going ahead with a very formal definition just now, because that is, you can see in the books. I just want to give you an intuitive understanding or a feeling of this, right? So like your normal vector, traction, these are all vectors in the way we learned vectors in high school. Right? So they are these vectors with a single direction and a magnitude. So these are basically vectors coming in from R3. So these are called as first order tensors. If you had just numbers, scalars, this is scalars. These are called as zeroth order. Okay. Things like stresses and strain, they basically opt on first order tensor to give you another first order tensor. So this is first, this is first. So you add 1 plus 1, you get 2. So stress is actually a second order tensor. If you had a kind of a tensor which, I don't know, let's call it pi. If it operated on a second order tensor to give you a first order tensor, so this is second order, this is first order. So this will be 2 plus 1 equal to 3. So this is third order tensor. Right? stiffness tensor operates on a second order to give you another second order. So this is 2 plus 2 equals fourth order tensor. So that's the general idea behind defining the order of a tensor. That you can have tensors of many different orders. This third order tensor is less known. I think you might have seen second and fourth order tensors. Third order tensor comes in handy when we work with coupled problems in magnetomechanics, electromechanics, and so on. So I think the second order tensors are quite common and from physics because they appear often. So we have a lot of interesting properties that we study just for them, and then we can generalize them to other tensors as well. So that's what I wanted to do just now. Just to the hosts again, Aman, the warning came again for meeting.
Yes, sir. So we are
Ending in 5 minutes.
technical team is here with us, but still they are.
Maybe it will automatically shut down again in a couple of minutes.
So, sir, we will have the break after that, and we will start again, sir. And in between, we will try.
Okay. Okay, so what I want to discuss is principal invariants. Of second order tensors. And they are defined using something called as a triple product. And I think you might have familiarity with that triple product, which is basically if you have three vectors, let's say A, B, and C, all in R3, then triple product is nothing but A, B, C. It's written like this, which is A dot with B cross 3. Right? So I'll just write down for defining principal invariants. We need to work with this interesting result, which is if you have U, V, and W, and if you have A, B, C, all in R3, let me just say a couple of things before I start writing the mathematical details. Okay. So the idea of principal invariant is that we want to find out the things that will not change no matter what happens to the coordinate system. So we want to find out how the tensor operates on quantities without on different set of quantities and give the same result. Right? So this is a very useful theorem that we want to use, and the theorem is like this. And I don't want to dwell too much on the mathematics of it. If you take a triple product of all the three vectors, so basically you're operating the tensor once and you're taking the triple product and dividing by the triple product of the original vectors, then this thing does not change. And now you might think that why is that important? I mean, this is a very raw mathematical result, but I think we can see a little bit later how that connects to physics a little bit later.
Yeah.
Yes.
So sorry sir for the trouble. Now the technical team has finally said that they have rectified it. Hopefully we will not get this time any stopping in the meeting. So
Okay, then let's go on. No worries.
you can share your screen sir.
Yes. I'm just trying to connect the other computer also. Just give me 1 minute. Okay. Am I audible? And is it okay?
Yes, yes, sir.
Shall we start?
Sure sir.
Okay. So welcome back after the tea break. We were discussing principal invariants of second order tensors. And the central idea was that we want to have quantities that do not change if we try to choose a different coordinate system, right? So what I'll do is I'll quickly explain a couple of things. So this is the first thing that we said, okay, this is a quantity that does not change. And this is referred to as I1. And this is called as the first principal invariant of a second order tensor. It looks like very long calculation, but if you see, this actually turns out to be trace of t. This is called as trace. And trace, there is another definition of trace which I think you can look up, but this is what we call it. Then the next invariant is basically instead of having operating t on one of these, operate on both of these, two of these. So tu, tv and w plus, let's say tu, v, tw plus u, tv, tw over uvw. And the third invariant is just all of that together. tu, tv, tw over uvw. So these three quantities for a second order tensor does not change no matter what uvw are and what the coordinate system is. So the first thing is called as a trace, it has a familiar description. The third thing is determinant of t. The second one is slightly longer. This is half I1 square minus trace of t squared. It's a slightly longer definition, but this is what it is. And these three invariants, I1, I2 and I3 of a second order tensor are very, very widely used across mechanics. And instead of using the tensor itself, we in many cases we just use them. Right, and then there are a lot of other concepts, and I encourage you to just go through the notes that I've supplied to see what else is there. But I think my main focus was for this particular session, the first half of today, was to introduce to you the concept of tensor in a more natural way, and hopefully you at least learned a couple of things about how vector spaces come about naturally. They're not very complex mathematical systems, they are just collection of certain objects with some properties. And then tensor is just a linear transformation of these vector spaces. We saw tensor like a stress or a strain or with a stiffness tensor, and we saw tensors of various orders. Now you can do a lot of algebra and a lot of calculus with these tensors. and this kind of will come about slowly, and we can look at few things later on. What I want to move on to is a little bit more mechanical aspects. Okay, so we'll end this topic here along with the notes that you have, and then we'll move on to a bit more, let's say, kinematics. Which is like the foundation for continuum mechanics or continuum physics. Okay, so there is the whole purpose of this part of the study is that we are going to deal with soft material. Okay, soft materials, and they, if you have a beam, let's say, okay. Just hold on a second. I think I have some trouble with my computer, but okay. If you have a beam, you might have studied beams deflecting, and these kind of deformations are easily expressed by one-dimensional theories. But when we have a complex soft material, let's say in some random shape, and we apply some stress and strain, very large forces, it can deform into very complex shapes. And trying to the whole idea of this, the second part is how do we describe the deformation correctly? What's the best way to describe this deformation? And that's why this idea of tensors and applied to continuum mechanics becomes quite important. Okay, so let's move on with it. And now this might be some repetition for some of you, but hopefully it will be useful. Just a good revision. So let's take a body, and we are dealing with solids just now. Okay, so this is what we call as a reference configuration, and this is what we call as a deformed configuration. This is also sometimes called as Lagrangian, and this is sometimes called as Eulerian. This is sometimes called as material description, and this is called as spatial description. Okay, so there are many different books with many different languages, but they all mean the same thing. So you have a body, we call it B naught, and this is the body B on the right hand side. And what we say is that, okay, there is a point, usually in this we denote it by capital X, and the same point after deformation here as small x, and the deformation function is small x is some function chi of capital X. Now this is Greek letter chi, and in a lot of books of continuum mechanics it is used, so that's why I'm using just to maintain the same terminology. So if you move on to some other book, you will be not surprised. And this chi has all the good properties, so that it is continuous, differentiable, one-to-one, whatever the nice properties of a function that we want. If you're dealing with very difficult problems like fracture or other things, then those properties need to be changed. But for our cases, it's a good function. So if you have a function like this that can take any point small x to capital X, then we can say that the displacement of a point, okay, we can ignore the displacement. Then we can do something that we call it. I'll explain the concept of deformation gradient, using two kind of views. Okay, and let me recap again what I was trying to say in the very beginning of this course, that the material that we are discussing right now is available in the books. So you can go ahead and read the books to get a lot more detailed understanding. My role right now is just to give you some insights of the way I have understood this material, and hopefully some of those insights can be useful for you to understand it better. Okay? So deformation gradient is something that is quite useful in describing this deformation, and people view it from different angles. So I just want to give you my understanding of how I look at it. So one of the angles is that inside this body, small x and this deformed and reference configuration, let's say we have a small vector. Okay. Small change, it is called as d capital X, and the same vector comes here as d small x. And then the points are linked by the deformation function, but these small vectors, now these are vectors in a vector space. Okay, so dx, d capital X is in the reference vector space, and d small x is in the current vector space. So these two vectors in the vector spaces are linked by this deformation gradient. So I'll just put an underline to denote a vector or a tensor. This over arrow is a symbol, is a thing I don't like. So there's a tensor called as f, which is called as a deformation gradient tensor. That basically links these two line elements. Okay, so these are called as line elements. And it's called as a deformation gradient because this capital F is actually a gradient of this function chi. Okay, so that's a more visual way of looking at it. There is also a little bit more mathematical way for those of you who have more mathematical bent, and that is that this function chi is a function of this vector capital X. Okay, the vector X, capital X, is just the position vector of this point. And now if we apply Taylor's expansion, Taylor series expansion on this function, so it's like take capital X and make a small change. That's a small change. And that will give you the same thing, chi of capital X plus gradient of chi with a small change plus higher order terms. Okay, and then you can say, okay, this gradient of chi dx, I bring it on the left side, and on the right side I have chi of x plus dx minus chi of capital X, which is, so this thing is basically, okay, so this thing is nothing but small x, and this thing is just change in small x, so small x plus dx. So this thing becomes d small x. And this gives us the same relationship again, that okay, if I call it f, then I get d small x is capital F d capital X. So you can look at it in a bit more mathematical way as well. It arises naturally from this Taylor series expansion, and you can also look at it from the more geometrical way that, okay, if you have a line element, then changes in that line element are captured by this deformation gradient. Okay, so the deformation gradient is a central tensor that is used for doing a lot of these calculations. And then what we do is we take something called called as a okay. There are some theorems that I don't want to go through, but basically you can decompose F as a rotation and a stretch, or a stretch and a rotation. Okay, so R is a rotation. So you can write a tensor in terms of these two multiplications. So if R comes before, then it is RU. If R comes after, then it is BR. So these are two different types of rotations. And then if you do, let's call CSF transpose F, and now this requires a little bit more knowledge of tensor algebra, and you can look it up. That gives you U square. You can also have B, which is FF transpose, and that gives you V square. Okay, so this is called as right Cauchy-Green deformation tensor, and this is the same thing but left. So these are just some things to know. This is very widely used at different places. Now we talked about F directly being linked to changes in the length line element, but it gives you a little bit more than that. So if you have area element, so if I go back to my reference configuration, this is the point capital X, this is the line element, but you can have an area element by two line elements. Okay, so what happens is if you have dx1 and dx2, then area is just cross product of dx1 and dx2, and this is often you can see that, okay, if you have two vectors in a plane, and if you take a cross product, you get a vector which is out of the plane. Okay, so it is given as capital N D capital A. So this capital N is a vector which is out of the plane, and similarly for deformed, you can have D small x1 cross product with D small x2, and that gives you NDA. Okay. You can have a third line element, and that gives you the volume, which is dx1 cross dx2 dot with dx3, which is also basically triple product dx1 dx2 dx3. Okay. And it is called as D capital V in the reference and D small v in the current. Right? So we already saw that deformation gradient can link the line element, but you can also link the area element and the volume element. So area element NDA is cofactor of F multiplied by operating on capital N dA, and the volume dV is determinant of F operating on D capital V. So you can kind of link how the lines, small changes in the length are measured, how changes in the area are measured, and how changes in the volume are measured. And once we know all this, then I think we can kind of construct all the different types of changes in the dimensions of a body when it undergoes extremely large deformation. So this deformation gradient tensor becomes like a central idea behind behind all our measurements in continuum mechanics. Okay, let me pause for a bit and see if there are any questions in things that we've covered so far.
Please be participating.
I can see somebody speaking. I couldn't make that out. Sorry.
Not yet, sir. Any doubt?
Okay. Okay, fine. Okay, so let's move on. Let me also just give you a little bit more. So this determinant of F is sometimes called as, is abbreviated as J, or it's also called as Jacobian in many different books. And cofactor of F is you might have seen cofactor of a matrix in a different context, but it is J F inverse transpose. Okay? So this is just something to remember, that these are the way you calculate things. Right. So now we know how to measure changes in the dimensions, and then you can do time dependent deformation and other things. These are just on top of this. What I want to move on, the next is balance laws. So the idea behind balance laws is that any physical physics-based process that happens must satisfy laws of physics. Okay? So our deformation must satisfy laws of physics, and there are different laws of physics, different quantities that are balanced. So basically, things that should always be true. So a few important ones are conservation of mass, conservation of energy, conservation of linear momentum, and conservation of angular momentum. Okay, so if you're dealing with a purely mechanical system, like let's say stretching a body, stretching a rubber balloon, then these things must always be satisfied with your with whatever you do. Okay? Then there are some extra things that come in. So, for example, if you also have electric field or magnetic field, okay, so then you will have Maxwell's equations. If you have electromagnetic fields. So these are an additional set of equations that you must satisfy to make sure that your problem is consistent. If you're dealing with, let's say, some process where energy is not conserved, or energy, or there is like let's say there is some friction, there is some heat transfer, then you must worry about second law of thermodynamics. So I mean, the question is why do we talk about this? The reason about this is that we want to express our quantities, whether it is forces or stresses or strains or density, anything that we want to measure in terms of these balance laws to make sure that we have the correct equations to solve. So I can give you a small example. Or maybe I can just kind of list how it looks like. Okay? So in the case of conservation of mass, you just need to look at basically density. So this is density in reference configuration, and then density in current configuration, and basically try to find out a way that they are connected. And a very simple way is that because we know how the volume changes, we know that the volume changes are captured by this determinant of f, the Jacobian. So we can simply say that because mass stays constant, let's say if mass is constant, then density times volume in the reference is the same as density times volume in the current configuration, or rho naught is just J times dV. J times rho. Right? So you get a very simple relationship like this. And these are the kind of simple relationships that we get from each of these balance laws in terms of the quantities that we are working with. Okay? So, for example, for the case of balance of linear momentum, when we're talking about balance of momentum, in the case of static, where we don't want to talk about velocity and everything, because we are just dealing with slow deformation. In the case of quasi-statics, we simply get that divergence of sigma, which is the stress, plus the body force equals 0. So this Cauchy stress, body force, and this is a vector equation, so the 0 is also a vector. So we get all these kind of relationship. For the case of balance of angular momentum, we get that in order the angular momentum is balanced, the Cauchy stress must be symmetric. Now, how that comes about, you can see in the book why that happens, but this is just a consequence of these laws. And these individual laws basically apply to individual physical quantities. So conservation of mass applies to density, for example. Linear momentum applies to internal forces, and internal forces are captured by Cauchy stress. Angular momentum also applies to internal forces, which is captured by Cauchy stress. When you're talking about Maxwell's equations, you might have, we will see them later on. So once we have written down our balance laws and we know how to express that information, I think the important bit that remains is what we call as constitutive equations. And constitutive equations are the ones that link stress to strain. Or link conjugate quantities. So you might have you might be dealing with thermal flux and heat flow. Then you'll have different conjugate quantities. For the case of deformation, you've got stress and strain as conjugate quantities. And for a very simple one-dimensional problem in linear elasticity, we have something like this. Sigma equals E epsilon, where this is what we call as the Young's modulus. Right? And this is a constitutive equation. It links stress to the strain. But when it comes to a more complex scenario that we are discussing right now, where sigma is a second order tensor, epsilon is a second order tensor, then we have to do a little bit more. So for example, in linear elasticity, we have already seen this thing, that the stress tensor is the stiffness tensor times the strain tensor. Okay, so this CIJKL, the stiffness tensor. Those of you who have done finite element method and linear elasticity might have seen this thing, that something like this. The stresses and strain linked by a stiffness tensor, which stays constant. Okay, so for linear elasticity, CIJK stays constant. Because in linear elasticity, the stresses and strain have a linear relationship. But in the case of soft solids, it's often nonlinear. So when you have stress and strain plots, you'll have something like this. And then CIJKL is no longer constant. And then we need to come up with a different way of describing this stress and strain relationship, right? So, and there are many different ways of doing it. The easiest and the nicest way is what we do now, but there are many different ways of doing that. Okay, so we'll discuss that part a little bit now. But before that, any questions at all? Okay, maybe I move on, and then we can see the questions. So I'll give you kind of a couple of examples on this. Right. So before I do this, maybe I just also need to explain one more concept, which is before we discuss how do we link sigma and epsilon together, I just want to talk about stresses, strain in different configurations. Okay? And this is something I think this is quite important from a more understanding point of view. And that's why I want to put a little bit more time on this. So remember we had this like reference with capital X here and a current configuration small x there. Okay. And when we talk about any quantity, any physical quantity, it can be expressed either in this coordinate system, let's call it coordinate system 1, or it can be expressed in this coordinate system, let's call it coordinate system 2. See? So these two different configurations are basically also two different coordinate systems, because the points, this capital X here is a position vector in this coordinate system, and small x here is a position vector in a different coordinate system. They might be the same, they might and they might be different. You know? So in linear elasticity, if you're not familiar with this nonlinear problems, if you're only familiar with linear problems and linear elasticity, then they are exactly the same. But in nonlinear problems, they are usually distinct, and it's important to make that distinction clear. So when I talked about this this tensor, deformation gradient tensor, capital F, it's a function of points in the reference configuration. And similarly, the Cauchy-Green tensor, which is F transpose F, again is a function of points in the capital in the reference configuration. So if I want to measure any changes in the length with respect to the reference configuration, which is on the left, I would use F or C. If I want to measure my changes with respect to this current configuration, then I would use B, which is a function of points in the small configuration because it is F transpose. Okay? And this all depends on points in the current configuration. So you can express this deformation with respect to the points either on the left in the reference configuration or with respect to the points either in the current configuration. The stresses, so you've got the Cauchy stress, this sigma, and this is expressed in terms of the current configuration. Okay, so sigma takes in normal vectors of the current configuration and it gives you the traction vector in the current configuration. So this is current and this is also current. Then you have something in the middle which is Piola stress, or more commonly known as first Piola-Kirchhoff, which is P of capital X. So what it does is it takes the normal vector of the reference configuration but returns the traction of the current configuration. Okay? So it's like reference and this is current. And then you have got second Piola-Kirchhoff stress, which is capital S of X, which takes in quantities in the reference configuration and returns the normal vector, the traction measured in the reference configuration. Okay, so this is reference, and this is reference. And I think I would just like take a pause to understand this thing a bit more carefully. So reference configuration is when the body is the way it was before anything happened. Current configuration is the configuration after it has been deformed and after all the stresses have been applied. But when we say that for example, when I'm talking about this traction vector measured in the reference configuration, what I mean is I don't mean that there is traction present when the body is undeformed in the reference configuration. What I mean is traction vector is still there in the deformed body, but with respect to the coordinates of the reference configuration. So it's like a coordinate transformation. It's not that the reference is stressed or there is the forces in the reference configuration. It's more like whatever the forces are there after deformation, I'm looking at the same forces, but with respect to the coordinates of the reference configuration. And this is a distinction that is super important if you are looking at continuum mechanics, because I see a lot of people making some errors during this discussion. So you can transform your physical quantities from one coordinate system to another coordinate system, and you can measure them in different coordinate systems, but you just need to be very careful how the transformation happens. Okay. So the transformation, for example, so I can tell you how these three things are linked. So the first Euler-Kirchhoff stress is linked to Cauchy stress by sigma times F, sigma times cofactor of F, which means it is J times sigma times F inverse transpose. And then the second Euler-Kirchhoff stress is basically F inverse times P. So it is J F inverse sigma F inverse transpose. So these are some relationship between these two stresses, and that basically means that you can express your quantities either depending on the way you want to do the calculations. You can express completely in the reference or completely in the current. And for solid mechanics, reference is preferred. You can do your mathematics in anything, but reference or Lagrangian configuration is preferred, especially when you're doing any finite element analysis, because the reference coordinate system is fixed. If you're applying a very large deformation, the current coordinate system can keep evolving as the deformation happens, but the reference configuration stays fixed. So it is a lot more preferable to use reference configuration for all the analysis, for all the finite element analysis and mathematical analysis. So we tend to use P or S depending on your preference, but I'm just listening. There's a fire alarm in my building. Just give me a couple of seconds to see if I have to leave. Aman, I think I'm sorry, but my office building has a fire alarm. I need to check. No problem. I need to leave now. I'm sorry about that.
Okay, we can restart.
I will message you on to find out if I can come back to my office again or not.
Sure, sir. Otherwise, you will conclude the today's session, sir.
Yes. Okay. Thank you. Sorry about that. There's a fire alarm. I have to just.
No problem, sir. Thank you.
Thank you.